So, we will see what is fault simulation. So, it is ultimately a piece of software. So, maybe it nothing to do with the actual hardware part of the circuit. So, this is for software which will be doing some simulation of the circuit in the presence of some faults. Okay. So, as an input it has got a circuit description. So, you can say circuit description in some level, maybe gate level, maybe module level, maybe RTL level. Okay. So, it is some description of the circuit, then a set of test patterns. So, this is given as input to the system and a fault model. So, like a set of test pattern, maybe I randomly generate say 100 test patterns for a circuit. So, if I have got an n input circuit, so any n bit random pattern is and it can be considered as a test vector for the circuit. So, if I have got n say 100 such patterns, so that becomes a test pattern set. Then a fault model. So, we have said that every defect in the circuit, so that is modeled as a fault. So, what is the fault model? Like staccato fault model, like single staccato fault model or multiple staccato fault model. Are we considering delay model, delay faults like bridging faults? So, like that. So, some fault model has to be specified, and then what the fault simulator will do, it will determine the faulty outputs, like under the presence of fault of a particular fault, which primary outputs of the circuit differ from their correct responses. So, that gives the faulty outputs for every test pattern and for every fault. And undetected faults, there may be certain set of faults which are not detected by the given test pattern set. So, that is the set of undetected faults, and once we have once we know how many such faults are detected by the fault test pattern set. So, we can assign a score to the test pattern set, which is known as fault coverage. So, naturally our objective will be that we will be using as small a test pattern set as possible. At the same time, we would like to have a very high fault coverage. These two requirements are contradictory, but we will see how these are actually achieved when we go to the chapter on test pattern generation. But for the time being, we are talking about determining the quality of a test set. So, what is the complexity of this fault simulator? It is proportional to n, the circuit size in terms of number of logic gates. So, because every gate has to be simulated for every test pattern, so it will depend on that. Then P is the number of test patterns and F is the number of modeled faults. So, it can be shown that the size say F is number of faults being proportional to n. So, if we are considering single staccato faults, then if I have got n lines in a circuit, then there are 2 into n possible faults in the circuit. So, that way the F becomes proportional to n. So, the overall complexity is n into F, n into P into F, and F if we replace by twice n. So, it becomes big O P n square, so of the order of P n square. So, as you are increasing the size of the circuit, the complexity of fault simulator that will go up significantly. As we are increasing the number of test patterns, then the fault simulator time increases in a linear fashion. The most simple fault simulation technique is the serial fault simulation. So, what we do in this case? We first perform a fault free logic simulation on the original circuit. So, we have got the test pattern set. For that test pattern set, we want to determine what are the fault free responses from the circuit. So, these are called good or fault free response. Then for every fault, we perform fault injection and logic simulation. So, we perform fault injection means we modify the circuit description as if that particular fault has got inserted into the circuit, and then we again simulate the circuit. So, in the presence of that particular fault, what is going to happen? So, that is the logic simulation after doing the fault injection. So, that will give us the faulty circuit response. Now, there are two possibilities, that for certain faults, for certain patterns, the faulty response may be same as good response. That means, those patterns are unable to detect those faults. So, for if it happens that for all the primary outputs, the patterns response is same as the fault free response, then those for that particular fault cannot be detected by that test pattern. Now, if it is detected by some test pattern, then naturally this faulty circuit response has to be different from the good circuit response. Sometimes that is called golden response. So, this is the way this serial fault simulation will work. We start with F. F is assigned as the collapsed fault list. So, we have seen that when we do a fault collapsing by taking the only the non equivalent faults. So, for every equivalency class, so we take only one particular fault. So, when we do this thing, so we get the collapsed fault list, and in the collapsed fault list we find out like it is often leads to the reduction in the number of faults. So, if number of faults reduces, then complexity of fault simulation will reduce. That is why start with collapsed fault list. Then we perform a fault free simulation for all patterns. So, test pattern is coming as an input. So, do a fault free simulation. So, then we pick up the faults one by one from the collapsed fault list. So, we pick up the next fault. So, as long as there are faults in the list, so we try to get we get the next fault F from the set of collapsed fault list, and then reset the pattern counter. So, we basically for this fault we again start from the very beginning of the pattern set. If my pattern set has got 100 patterns, then for all these 100 patterns we would like to simulate under the presence of this particular fault. So, we see that we get the next pattern, and then we get the next pattern P and do fault simulation for P. After doing the fault simulation, if we find that there is a mismatch in the sense that the fault free response and the faulty response under the presence of this particular fault is different for pattern P. If it is so, if there is no mismatch, that means this pattern could not detect that fault. So, we try with the next pattern. However, if it can detect that fault, we delete F from the set of collapsed fault list, because for this fault we have identified, we have got one pattern that can detect it. So, there is no point in keeping it into the set F, because ultimately we are going to see whether the given test pattern set is covering the collapsed fault list or not. So, since this fault small f is already detected, so there is no point simulating it again for the remaining test patterns. That is why this is deleted from this set F, deleted from this set F, and then we try with the next fault. So, this way it continues. Okay. So, this is a very simple algorithm, but time consumption is high. So, this may be an example, like say we have got this particular circuit. So, we want to see that whether we can get this thing, that is F stuck at 1 and G stuck at 0. So, these two faults. So, primary input patterns, we have got 3 patterns, okay, P1, P2 and P3, and for them this ABC value, this is, so P1 is 0 1 0, P2 is 0 0 1 and P3 is 1 0 0. So, for first one is for the good circuit, what is the response? So, we simulate this circuit for in the absence of all these faults F and G, and we see that this K good is 1 1 and 0 for the 3 patterns. Now, if we assume that the fault F is present in the circuit, then what will happen? So, this in the absence of fault, line H was equal to 0. Now this line is stuck at 1. So, this line is 1, and this B and C both are at least I think one of them is 1. So, B line is 1 for the first pattern. So, this OR gate is 1. As a result, this H line becomes 1. So, this K becomes 0. So, under the presence of fault F, the line K gets the value 0. So, there is a difference from the good response. Okay. So, this is a good response is 1 and this is 0. So, we say that this pattern P1 can detect this particular fault F. Also, when we try with pattern 2, we see that the response is different from the good circuit. So, good circuit response is 1, bad circuit response is 0. So, that way there is a difference in this. So, that way we have got a faulty response for this fault as well for pattern P2. So, either P1 or P2 can be used for detecting this particular fault. For P3 also, we see that the good response is 0. However, P3 could not detect this particular fault, because the faulty response for P3 is also 0. So, it cannot detect this fault. However, this it can detect the fault Kg. Okay, so Kg is 1. You see, one unique thing about P3 is that P3, out of these 3 patterns, P3 is the only one which could detect the fault G, whereas this P1 and P2 could not detect this fault G because their faulty response is same as the good response. So I can, so if I am asked to do a choice from this pattern set P1, P2, P3 for detecting the faults F and G, so I definitely have to include P3 in my set, whereas from between P1 and P2 I can have only one of them. Next we discuss about a concept called fault dropping. So basically we want to halt simulation of the detected fault. So that is the thing known as fault dropping. Like in this particular case, we have to simulate P1. Suppose in this previous example that we are considering, having 3 patterns P1, P2 and P3. Suppose we are simulating in this particular order, P1 followed by P2 followed by P3, and fault F is detected by P1. So it is not necessary to simulate P2 and P3 for F again, because we know that fault F is already detected. So this is known as fault dropping. So we drop F from the simulation further simulation of patterns. Now most faults are detected are relatively they are detected after relatively few test patterns have been applied. So this is a general observation, like if you have a circuit and if you see the test patterns, successive test patterns and their detection of faults, initially as you increase the pattern set size, so your fault coverage increases rapidly, because many of the faults that we have in the circuit, so they are random pattern detectable faults, because they can detect, so any random pattern can detect those faults. So we will come to this issue, whereas so that way this the possibility of this fault coverage, so that increases when we have got this thing. Now when we have another part, when we have got this large number of patterns, now for remaining patterns, so it may not be very much effective in detecting many of the faults. Okay, so for fault, so this fault dropping will help us, because those faults are already detected, so we do not simulate them further. However, there is another application of this fault simulation which is known as diagnosis. So diagnosis is actually a process by which after we have done the manufacturing and we have passed it through a test session, suppose the chip fails. So for when the chip fails, we collect all the faulty responses and try to see what may be the possible reason for this failure. Now you see, if you have got only one pattern detecting a fault and we just note that one only, then due to this equivalency of faults, what can happen is that this particular fault may be detected by many other patterns, and this particular pattern might have detected, could have detected many other faults. Now a better situation that can help us in pinpointing the exact location of fault is that if we have got a full history, like if we have got for the entire test pattern set which are the patterns which have failed. So if we know that pattern number P1, P10 and P15 have failed, and if we know all the faults that could be detected by P1, P10 and P15, then we may try to find out what is the common between all these faults, and if depending upon that we can try to get some confidence about the location of the fault. So that way, if this fault dropping is good for fault simulation, but when we are looking for diagnosis type of application, this fault dropping is avoided. So serial fault simulation, it is easy to implement. As you have seen, the algorithm is very simple, and it has got ability to handle wide range of fault models like stackered fault, delay fault, bridging fault. So like that, it has got ability to handle wide range of fault models. Disadvantage, of course, it is very slow, because it is of the order of p into n square. So that way, if the pattern set size is large or number of lines in the circuit is large, then it will take a lot of time for doing the simulation. So people have started looking for faster version of this fault simulation process, and accordingly many other simulators have come up. So one of them is known as parallel fault simulation. So, again the same thing as we were talking in this logic simulation part, that we have got this bitwise, we have got this word sizes of this processor or the computer on which you are running the fault simulator. So, possibly you can do some parallel simulation. So, you can use this word of a computer to represent many possible status of these signal lines in the circuit, and then maybe if I have got say 32-bit word, then I can do it like this, that for 32 different status of a single line can be put into a word. Okay. So, that way it can help us in doing the simulation process. Now, there are two variations that are possible. One is known as parallel fault simulation, and another one is parallel pattern fault simulation. So, these are the situation, like if I have got say a W bit word, if I have got in my computer, suppose it is a 4-bit word. Okay. Now, for every signal line that we have, so we have got this particular word available. Now, suppose this is one AND gate. So, it has got two input, and with both the inputs we put this 4 bit. Similarly, at the output also we have got this 4-bit space. So, the idea is that if the first bit will be computing AND of this and this. So, when these two are ANDed, the result will be stored here. Similarly, when these two are ANDed, result will be stored here. So, by doing a bitwise parallel operation, so I can do this AND operation of 4 bits simultaneously. Now, what do we represent in this 4 bits? So, that is one important thing. So, one possibility is that in parallel fault simulation, so we represent these individual bits different faults. Okay. For the same line, if in the presence of say 4 different faults, what are the values of these what are the values of these line? So, accordingly we get 4 different values for the same signal line. So, that is the theory of this parallel fault simulation. Another one is parallel pattern fault simulation. So, here we are simulating for a single fault, but I take 4 such patterns and combine them into one chunk and do the simulation together. So, both the versions are available. So, we will see them one by one. So, first one is the parallel fault simulation. It is assumed that we use binary logic, that is one bit is enough to store logic signal. So, we are not looking into ternary or this higher order logics, but only binary logic. So, if we have got another W bit word data word, then for parallel simulation W minus 1 bits are dedicated for faulty circuit and 1 bit is dedicated for fault free circuit. So, what will happen? So, I will have W minus 1 faults simulated simultaneously, and the first bit is taking the fault free circuit. So, that way we can process faulty and fault free circuits in parallel using bitwise logic operations. So, this is an example. So, you see this is the original circuit. Okay. So, it has got 3 inputs A, B and C, and what we do? So, we have got 3 with every line we associate 3 bits. Okay. One is that we have got this for line A, we have got the good circuit value, that is 0. Then we have got, if this line is stuck at 1, this A stuck at 1, then what is the value? So, that is there, and the other fault is G, which is J stuck at 0. So, if J is stuck at 0, what is the value of this line A? So, what we do, this particular fault we replace as by an OR gate, where one input is A and the other input is 0 for good circuit, 1 for the fault A stuck at 1 and 0 for the G stuck at 0 fault. Now, you see that when we are when we are evaluating this OR gate, since A gate in good condition, A line in good condition, the value is 0. So, this point you get 0. So, that is actually the circuit remains functionally same as the previous one under fault free condition. Whereas, in the faulty condition, so this one F stuck at 1. So, this will become this OR gate output will become 1. So, that way we are getting the value that F is stuck at 1. So, that way it is actually modeled. So, these new gates are introduced GF and GG into the circuit. So, into the logic circuit we are introducing these new gates GF and GG, and we have got this 3-bit words holding the good circuit, F faults and G fault and the consequence. Now, you see for B and C, so we have, so now in the circuits, if you apply different patterns, so you can simulate this circuit in a logic simulation fashion and get the responses computed. So, this three faults, one good circuit and 2 faults, these three circuits are getting simulated simultaneously. So, this is the situation, that is, suppose I have got this pattern P1. So, pattern P1 under fault free condition, A is 0, B is sorry, A is 0, B is 1 and C is 0. So, that is the fault free condition. Now, when we simulate, so this under this faulty condition, A will become equal to 1. So, under fault under F, under the occurrence of fault F, A will become equal to 1, this will become equal to 0. Now, when you are computing, say E, say this value, say H. Okay. So, when you are doing this thing, so L we are directly doing, we are doing a bitwise ANDing 1. So, that way it is getting the internal values. So, so we can see that by doing a bitwise operation, we can directly simulate the fault. We are directly simulating the circuit for a particular pattern, but for 3 cases: fault free, fault F and fault G. Similarly, for pattern P2, again we can do a simultaneous simulation of fault free, fault F and fault G. So, that way. So, ultimately, so the amount of effort needed will be reduced much, because many of the operations are being done parallelly. So, several faults are getting simulated parallelly. Advantages: we have got a large number of faults that are detected by each pattern when simulating the beginning of the test sequence. So, as a result, what will happen is that since every simulation, since it is handling a number of faults instead of a single fault in case of serial simulation or series fault simulation, now fault dropping may be very effective, like very easily many of the faults will get dropped, okay, because of this parallel fault simulation. So, each pattern is simulated directly for all the faults in one shot. So, that way the fault dropping will be higher. Disadvantage: it is applicable for unit or 0 delay model. So, unit delay model means all gate delays are assumed to be equal to some unit value. Okay. So, that way it is under these 2 models only. So, we can do this thing, otherwise we cannot take care of these different delays, because then the structure will become more complex. Second important problem that we have is that the faults cannot be dropped unless all W-1 faults are detected. So, because the structure of the computer of the processor word that we are using, so there itself we are putting W-1 faults. So, there is no point dropping a fault here, because anyway you will be doing W bit logic operations over these bit patterns. So, that way you cannot really help in dropping the fault. So, if all W-1 faults have been detected, then you can drop it. Then you can say, okay, I will construct a new word size, new word consisting of a different set of faults, and that way it is better. But ideally, otherwise there is fault dropping is difficult. Next, we look into parallel pattern fault simulation. So, where in the previous case we are trying to simulate a number of faults parallelly. Now, we will be doing single fault simulation, but for multiple patterns. Okay. So, again the basic idea is similar. So, we have got, say, W bit data width, then W test patterns are packed into a word and simulated for the fault free and fault free or faulty circuit. So, now at one time only one particular fault or the good circuit will be simulated, but we are packing W test patterns into the word. That way the operation becomes parallel. Now, it is a single fault. Okay. So, naturally single fault will be handled at a time. First a fault free simulation will be done, and then for every fault we will do a fault injection and faulty circuit simulation. Now, here we have got the advantage, because in one shot we are getting, for a particular fault we are getting a large number of patterns that can detect that particular fault. Okay. So, this way we can we can do fault dropping, and also this faulty, many of the patterns are being simulated simultaneously. So, it will be saving the effort. So, this is the flow of the algorithm. So, start with the then we start with the collapse fault list. So, new W patterns. So, as soon as we get a new W patterns from the test set, so we apply the next W patterns, and output good is the good circuit outputs. So, this is basically a the fault free simulation. So, we take the next W patterns and do a fault free simulation. Now, for these W patterns, so we will try to simulate for each of the faults. Okay. So, we take the next fault. If the fault if the next fault is there, some more fault is there, so we get the next fault F from the collapsed fault list. Then we remove the for last fault and inject fault F. So, in this circuit, previously some fault may be existing, or if it is a good circuit, then there is no fault. So, we will inject the new fault F into it. Then we simulate the circuit and see what are the faulty circuit responses for W pattern. So, OF is the faulty circuit response for W pattern. Now, if OF and O good they are same, then the faulty circuit none of the faults could be detected from this. Otherwise, so this particular fault could not be detected from if it is, if they are not same, if the faulty response and good response are not same, that means this fault was detected by some pattern in the W set. Okay. So, in that case we delete F from F, that means we have detected this fault. So, this fault need not be considered anymore. So, we take the next fault, this process continues. Okay. If OF and O good are same, fault free faulty response and good responses are same, then this set of W patterns they could not detect this particular fault. So, it will try with the next fault and try to do that. And when this F becomes empty, when we have when there is no more fault that we can handle, then we go back and try to get the next new W pattern. So, for one set of W patterns we consider, say, then for that we simulate all the faults, then we take the next set of W patterns and simulate the next set of faults. We will continue in the next class.